Welcome to The Explainer. Look, if you're a focused learner trying to master the foundational building blocks of mathematics and you want to skip all the unnecessary fluff, you are in the absolute right place. Today, our goal is pretty straightforward. We're going to take what often feel like these incredibly dense, abstract mathematical definitions and completely break them down into simple, tangible examples. We're basically going to build your understanding layer by layer, starting from the most basic concepts and working our way all the way up to a pretty famous mathematical function. Okay, let's dive right in. We're actually working directly from some authentic, handwritten source material today. And honestly, there is just something super cool about looking at raw, hand-drawn math notes. We're going to use this exact page to uncover the logic of sets, step by step. Our game plan is to read the definitions straight from the source and then immediately ground those definitions using the exact examples the author provided. So here's our roadmap for today's explainer. 1. Introduction to sets. 2. Measuring sets with cardinality. 3. Sets within sets or subsets. 4. Exploring the power set. And finally, number 5, Euler's Phi Function. All right, part 1, Introduction to Sets. Let's kick things off with the absolute foundation. What exactly is a set? Well, the source defines it perfectly. A set is simply a collection of well-defined objects or things. The absolutely crucial part of that definition is well-defined. A set isn't just a random pile of stuff. It's a crystal clear collection where you can easily and objectively say, yes, this belongs in the group, or no, it doesn't. It's literally the fundamental way we organize information in math. And this brings us to our first rule, taking that abstract definition and applying it to a concrete reality. The author creates a set named S and fills it with specific, well-defined objects, A, E, I, O, U. Because we all know exactly what the English vowels are, right? There is zero ambiguity here. It perfectly satisfies our definition of a well-defined collection. Moving right along to part 2, measuring sets, also known as cardinality. So now that we have our set, let's look at the formal rule for simply counting what's inside it. Cardinality is defined as the number of elements in any set S. Notice how it's denoted by putting the letter of the set between two vertical lines, kind of like absolute value bars. Now, I know the word cardinality sounds highly technical, but it's really just a fancy mathematical term for asking, hey, how many items are actually in this box? Let's immediately apply that definition to our vowel example, set S. If we simply point and count them, A, E, I, O, U, that's 1, 2, 3, 4, 5. We found our answer. The cardinality of our set S is exactly 5. You just counted the elements, which means you literally just determined the cardinality of a set. Okay, part 3, sets within sets, otherwise known as subsets. Now that we know how to group items and count them, let's look at finding groups within groups. Our source material defines a subset like this. Any set A is called a subset of B if each element of A is also an element of B. Basically, the formal definition is telling us that a subset is just a smaller collection entirely contained within a larger one. But remember, if even one tiny piece of the smaller set is missing from the bigger one, the rule breaks and it's no longer a subset. To anchor this in reality, let's look at the author's exact example. We have a brand new set, set T, which contains the letters A, E, I. Now let's compare that to our original set S, which is A, E, I, O, U. We can clearly see that set T is a subset of set S because every single letter in T, the A, the E, and the I, also lives right there inside set S. It's a perfect match for our definition. The notes also give us this really awesome, broader mathematical example. In standard math notation, Z stands for integers, right? Whole numbers. Well, the source shows how this set of Z is a subset of Q, which are rational numbers, R, which are real numbers, and C, which are complex numbers. This brilliantly shows how this simple groups within groups logic actually applies to the entire universe of numbers. For example, the integer 2 is also a real number, 2.0. Therefore, every single integer lives inside the larger set of real numbers, making integers a subset of reals. It's the exact same logic we used for the vowels. Part 4, exploring the power set. Let's really level up our understanding here by exploring a set made entirely out of other sets. Here is our definition. The collection of all subsets of a set S is called the power set of S. This rule tells us that if we gather up every single possible subset we can make from a given set, and yes, that includes the empty set and the set itself, and we put all of those subsets into one giant master set, we've created a power set. It's an incredible concept of nesting data. But you might be wondering, how big does a power set actually get? Well, translating this to the formula from the notes, we see the cardinality of a power set is 2 to the power of the original set's size. Let's think back to our vowel set, which had 5 elements. That means its power set would have 2 to the power of 5, or 32 different subsets. That giant master set would include everything from a tiny subset with just A and E to the entire set of all 5 vowels, making 32 unique combinations. It just goes to show how insanely quickly things scale up in set theory. And finally, part 5, Euler's Phi Function. For our final structural pillar, we're going to apply this grouping and counting logic to a much more complex formula, Euler's Phi Function. Now, do not let the mathematical notation here intimidate you. While this string of symbols looks super complex, let's just read the rule like a sentence based on the definition in our source. It simply asks us to create a set of natural numbers, represented by x, that are between 1 and n. But here's the catch. Those numbers must share a greatest common divisor, or GCD, of 1 with n. In simple terms, they can't share any factors with n other than 1. Once we have that specific set, those vertical bars on the outside tell us we just need to find its cardinality. Basically, we just need to count them. Let's break down the reality of this with the first example from the notes, finding phi of 6. Step 1, we look at the numbers 1 through 6. Step 2, we throw out any numbers that share a factor with 6. Well, 2 shares a 2, 3 shares a 3, 4 shares a 2, 6 shares a 6. That leaves us with exactly 2 numbers, 1 and 5. Boom, we've identified our set. Step 3, we calculate the cardinality. We literally just count them, 1, 2, giving us a final count of 2. See, it's really just defining the rules and counting. Applying this exact same sequence to the final example in our source, phi of 9, we look at the numbers 1 through 9. We eliminate anything that shares a factor with 9, which are basically any multiples of 3. So we drop 3, 6, and 9. What are we left with? The set of 1, 2, 4, 5, 7, and 8. We discover a set of 6 numbers that perfectly fit our condition. Then we take the cardinality, making our final answer 6. And there you have it. We went from the basic definition of a collection of objects all the way to executing Euler's function, all using the exact same logic. As we wrap up this explainer, I want to leave you with a thought about the sheer exponential power of sets that we learned about today. If the cardinality of a power set is 2 to the power of the original set size, how incredibly massive does a set of subsets become when you start with just a few dozen elements? It is a staggering thought to ponder for your next mathematical deep dive. Thanks so much for learning with me today.